Hello, everyone. Thanks for listening to our talk. So you can read the official title of the talk at the screen right now. But there's also an unofficial title of this talk. It would be ProxySQL and Orchestrator at MessageBird. This talk will be in two parts. The first part, explaining service discovery and failover. This will be done by me, Jean-François, who designed and implemented this infrastructure in 2018 and 2019. And then the second part will be discussing lesson learned and optimization to the infrastructure by Art Van Skeppingen, who is still maintaining this infrastructure at MessageBird. So let's dive in. So my name is Jean-François Gagné. I'm a MySQL expert and system engineer, but I'm not working at MessageBird anymore. I'm now working at HubSpot. At HubSpot, our mission is to help organizations grow better. We are a strong believer in the inbound marketing methodology, which is waiting for customers to express interest in your product before marketing to them. The opposite would be outbound marketing, which is spam emails, cold calling, and people ringing your door to sell you a random thing. And like nobody likes that. So we provide online services to support the inbound marketing methodology, including a CRM and adjacent hub tooling. You can visit our website if you want to know more. And obviously, HubSpot is hiring. Like, you can contact me if you want to know more. So this talk is about MySQL service discovery at MessageBird. So like, here's a diagram of this, and it's a little complicated. You don't fully understand what it is now, but my goal is for you to fully understand this diagram at the end of the talk. So there's a lot of things that went in there. There's previous experience from me at previous employers, and things that happened. I also thought a lot about this, and I want to share with you what brought me to design this. So first, I'll explain a little theory about MySQL high availability. I'll talk about a war story that taught me a few things and that I take into consideration when I built this, this service discovery. I'll talk a little about MySQL at MessageBird, and then we'll dive into service discovery using ProxySQL. And then at the end, I'll talk a little about orchestrator integration and the failover process. So MySQL primary high availability is a problem that a lot of people try to solve. There's a lot of solutions, and my favorite solution is to failover to a replica when the primary fails. But it's not as easy as it sounds, and it's quite hard to automate well. GitHub as a blog post about their complete failover solution. So you can read it if you want to know more. So I've been working with MySQL for a long time, and for about 8-9 years. And I've thought a lot about MySQL primary high availability. I wrote a blog post about it. And the summary of it is it's a process in 5 parts. So you need to plan what you're doing when you'll have an high availability event. You need to decide when you fail over, when you apply your plan. And this is failure detection. You need to tell the application that something changed, that there's probably a new primary somewhere. So this is service discovery. This is the subject of this talk. You need to protect again the limit of failure detection and service discovery to avoid split brain. And I call this fencing. And if you're not able to protect well enough, you have to fix your data if something goes wrong. So we'll quickly see what each of these imply. So failure detection is the first part and the first challenge of failing over. It's a very hard problem. A lot of thought have been put into research and thought about this. And it's a hard problem because you have partial failure, you have unreliable network, you have network partitions, and all these things to consider. So it's impossible to be 100% sure of a failure, and confidence needs time. So quick failure detection is unreliable, and relatively reliable failure detection implies a very long downtime. And we don't like long downtime. So quick failure detection for short downtime will generate false positives. So you will detect a failure, but there's not an actual failure. So repointing is the second part of failover. It's relatively easy if you have the right tool, but the complexity of this grows with the number of replicas. So there's a few software that you can read about that would help you with repointing. And by repointing, what I mean is when the the primary fails here, we have two replicas of this primary. And so one of them will be the new primary and the other will be a replica of the new primary. So you need to repoint, resource, or reslave the one of the replica to the new primary. So service discovery is the third part and the second challenge of failing over. If centralized, it's a single point of failure. If distributed, it's impossible to update atomically. And so either service discovery will introduce a bottleneck with performance limit, or it will be unreliable in some ways, like pointing to the wrong primary. And this is the problem of the next part. So some ways to implement service discovery has been discussed by Shlomi. I invite you to read this blog post to know more about different ways of implementing service discovery. But unreliable failure detection and unreliable service discovery is a recipe for split brain. So this is messing up your data because you're writing at two places at the same time. And so we want to protect against split brain with fencing. And this is an advanced subject, not a lot of solutions have been discussed for that. Proxies and semi-synchronous replication might help. And this talk is about proxies helping to implement fencing. So if you end up with a split brain, you need to fix your data and only you can know how to do this because this is your data. So I'll give a tip about this on the war story. So our failover war story starts with two data centers and two zones in those data centers protected by a firewall. And service discovery here is DNS and failure detector is Orchestrator. So everything goes well. We have the primary in zone 1. It's replicating to a replica in zone 1 and one replica in zone 2. So this is crossing the two data center. And there's a second replica in zone 2. But things start to go like the first event here is the firewall failing. So this is problematic. Our primary is inaccessible right now. So we just fail over to zone 2. So the new primary is in zone 2. So we do all what is needed to promote the replica to primary. We stop replication. We set it read-write. We update DNS. And then everything is OK. We're back up. Everything is working. But then the firewall comes back up, which at first is no detectable problem. But as I was the one reacting here, I got some intuition to say, hey, let's check the MySQL database in zone 1. And I found transactions in there that with the timestamp of after the firewall comes back up, which is problematic because this is also after the failover. So this is kind of a split brain situation. We have writes on both places. And this is problematic because the writes in zone 1 hasn't reached zone 2, the write after the firewall came back up. So we have data that is only in zone 1 and not in zone 2. And these transactions are sharing auto increments that has already been used after the failover in zone 2. So if things fail at auto increment 100, zone 2 consume 101, 102, and so on. So maybe zone 2 is now at 200. And those writes in zone 1 reuse the same auto increment, 101, 102. So now we have data that has duplicate auto increment. So luckily, there's only a few transactions. But what happened? So to understand what happened, we need to have a little more details about this infrastructure. So DNS, as service discovery is it is not very detailed, but we have DNS servers in each of those zones. We also have web servers in each zones. So when the firewall came back up, the web servers took some traffic in zone 1. And because DNS in zone 1 was not updated yet, the web servers in zone 1 wrote to the database in zone 1, which explains why we have a few transactions there. And then a few seconds later, this DNS was updated. And so then the writes went to zone 2. And then like the split brain situation like disappeared. But like for a few seconds, we wrote in zone 1, which like was problematic to fix. So like this is basically a war story around a decentralized service discovery causing problem because it wasn't updated everywhere at the same place. And like this is a complex infrastructure that we didn't fully understand what happened, and we didn't foresee this situation. And so like there's something you need to remember about failing over is sooner or later you'll have a problem. So you need to be able to fix things if things go wrong. So you need to be ready for this. So I'm sharing this war story to like help you design your infrastructure. Like GitHub also shared a war story that happened to them with MySQL, so you can read it. I shared another war story in another talk. So please also share your war story. So like the collective knowledge about these things can improve. And so I told you that I would give a tip to ease data reconciliation. So in this case, the problem was auto increment. So right now, like my thought about auto increment is that they should not be used. We should use UUIDs instead. But we should store UUIDs in an optimized way. So like you can read these 2 blog posts about this. And my other war story is also like part of it is also about auto increment causing problems. So one day, like I might write a blog post or I might do a talk about the dark side of auto increments. Like this is not the subject here, so I'll move on with service discovery. But like auto increments right now isn't part of the features of MySQL that I don't like a lot. I think it's a footgun feature. Like it can be problematic and it causes problem. So MySQL at MessageBird. So like MessageBird is using MySQL 5.7, more precisely Perk on a server, hosted in different Google Cloud regions. And there are 3 types of MySQL deployment at MessageBird, depending on like, can the primary be in more than one region? So the first type is multi-region primary. So the primary can move from one region to another. The second type is the primary sticks to a single region. And we have replica in this region and in other regions. And the third type is a special case, the second type, like no replicas in other region. So here, this is an orchestrator screenshot of a deployment at MessageBird. So the primary here is on one region. It has 2 replicas in 2 different regions. So the failing over will be cross-region. And then we have many other replicas in potentially even more remote regions. So like the story here is that the primary is in one European region, the 2 replicas are in 2 other European regions, and then we have even Asian and US regions hosting replicas. So the requirements for like MessageBird service discovery was to be able to route traffic to local replicas because we want to take advantage of local data to have fast reads. And because I saw in the past problems around fencing, I want to embed some fencing mechanism in the service discovery that I was implementing. So this led to a multi-layer solution using proxies. And in this case, this is ProxySQL. And these 3 layers are collect, master gateway, which will be abbreviated MGW, and fencing. So there's a special case for single region, primary, master gateway, and fencing are merged into local fencing, which I will like abbreviate blockfan. So now this diagram starts to be a little more, to make a little more sense. Like we can see the collect, master gateway, and fencing layer before going to MySQL, like a primary in one European region and 2 replicas, which are the standby primary into other European regions. So we'll now go in details of each of these. So at the high level, collect is the standard like entry point design. Like we'll talk a little more about this, but this is like the entry point of the system. Fencing, the last part, is the natural way to route traffic to the primary. And it's also a way to fence the primary. So it's hosted on different nodes. So when the primary fails, we're able to tell fencing not to route traffic to MySQL to actually do fencing. Master gateway is the glue between collect and fencing. We'll talk about this a little more. And lock-fen is actually just master gateway and fencing merged. Like when the primary cannot move from one region to another, like it is a symbol, it's a simpler problem. So we don't need like master gateway and fencing. We can merge everything into lock-fen, sorry. There's one difference between fencing and lock-fen. Fencing only has 2 ProxySQL, lock-fen has 3. We'll see why a little later in the talk. So collect, like it's very classic. It's a load balancer. It's a Google load balancer in front of 3 ProxySQL nodes. I like 3 because it's n+2i availability. So if one node fail, like I don't need to fix it in a rush. Like 2 nodes are able to take traffic, and I'm able to like add another node failing. So in this case, 1 node should be able to take all traffics. So from here, the read-only traffic is directly sent to replica. And the primary traffic, either read or read-write, is sent to master gateway or lock-fen, with the routing being specified here. So routing from collect to lock-fen is either local if the primary is local, or across a region boundary if we're in a remote collect of lock-fen. For master gateway, if we have a local master gateway, the traffic is biased there, and it's also sent to the other 2 regions with smaller weights. So ProxySQL routing is weight-based, so there's no way to do a fallback mechanism. So like we can put a weight of 100 or 1,000 to local and a weight of 1 to the remote. Obviously, US or Asia to Europe like is sent like to any of the 3 master gateway. It's not important at this point. We don't know where the master is, so we need to route the traffic closer to the primary from US or Asia. And like this closer to the primary, the first step is master gateway. So master gateway is deployed on all regions potentially hosting a primary. And like the design is an extension of lock-fen. So lock-fen is out to like the smaller possible set to repoint to a new primary, which is 2 nodes. And master gateway is the smaller possible nodes to repoint in case the primary is changing regions. So the way this is done, like this is bounding the update scope of moving a primary to one region to another. We basically want to avoid a planet scale reconfiguration of collect on a failover. So we don't want to reconfigure all collect in case we fail over. We just want to reconfigure a smaller set of node. And in this case, it's only on a continent. It's not a planet scale problem. Like it doesn't involve Asia and the US, only Europe. So we have a latency consideration here. And it also protects against network partition. We'll come back to that. So the routing from master gateway to lock-fen is if the primary is in a remote region, so on both 2 sides, we route to fencing. So lock-fen is in front of the primary. Master gateway knows in which region the primary is. So if a master gateway is not in the same region of the primary, it's routing to the lock-fen primary. And if the master gateway is in the same region of the primary, it's routing to the neighbors. And so what this means is that there's no direct path to the primary that is not crossing a region boundary. So local accesses in that middle region cannot go to the primary, like just routing in that data center. It will go out. And like this has an interesting trade-off. It sounds suboptimal, but it has the side effect of making the best versus worst case ratio of the round trip much closer. And what I mean here is if you're not crossing a region boundary, the best case is basically you can access the primary like in the scale of 1 millisecond because you're local to the data center. But if you need to access a primary out of there, it will take 20 milliseconds. And so your ratio is 1 to 20. And if you always cross a region boundary, the best case is 20 milliseconds, the worst case is 40, maybe 60 milliseconds. And so it's a ratio of 1 to 2 or 1 to 3. And that smaller variance helps a lot. So here is the worst case scenario, which could be avoided with smarter routing. So like having this smaller ratio is very interesting because it's moving the average closer to the median, and it avoids like an optimization that people could do to route local traffic. And in a previous setup, I had a lot of problems when we started. We first were at the local data center and a standby data center for disaster recovery. And when we started to move primary from one data center to the other, some applications started to misbehave because they were assuming that the primary was always close. And there was a conscious choice here to avoid this best case scenario to make sure that we wouldn't have problem with this. And it also prevents of writing the primary in the case of a network partition. So like, I think this has an interesting trade-off. I agree it might not fit everybody. And here we clearly see that there's no path to the primary in case of a network partition. So I talked about 2 fencing node versus 3 log fan. So I like n+2 high availability. And so like if a node fails on a Friday evening, I can wait until Monday morning to fix things because I know I have 2 other nodes. And if one of these 2 nodes fail, everything is good. But it looks like log fan is not n+2 high availability because if one node fail, like we only have like 1 node taking traffic. So it looks like we can like suffer like a downtime if another node fail. But in this case, what we do is like we just switch, like we fail over the primary on another region that has 2 healthy nodes. And actually, like I prefer having only 2 nodes. I don't like to have 3 nodes in log fan because it makes it more complicated to reconfigure in case of a failover. And failing over like is like quite simple in this case. Like detect a failover with Orchestrator, fence a primary, setting it at offline hard in ProxySQL, like doing all the regrouping, repointing, waiting for catching up, stopping replication, setting it read-write, starting heartbeat if you have it, and then updating ProxySQL to point to the new primary, and then you're back up. Like, and then you need to reconfigure fencing and master gateway if needed. And what I mean by that is, like here after a failover, like maybe we're crossing an additional region boundary, which is clearly suboptimal. So here we want to reconfigure master gateway. And the first step is to configure fencing on the remote region, reconfigure master gateway in the other region than the primary to point to our new fencing, and then reconfigure like the other master gateway to route traffic to its neighbor. And then we can clean up. And so like the reaction to a network partition is similar. Like if we have a network partition in the region where the primary is, we will reconfigure, or we will fail over to one of the other region, and we don't have any writes going through. So like that's why like I like this. Like there's a protection against network partition in this design. So Orchestrator integration is pretty straightforward. Like the pre-failover hook is to fence the primary in fencing or log fan. The post-failover hook is updating fencing or log fan to the new primary, and you're done. Like obviously, like this is like said in a simple way. Like the script that is doing that is complicated because it needs to take into account all possible failure scenarios. Like if I'm not able to contact one of the nodes, what do I do? Like I roll back my failover and I don't fail over. Like the implementation is a little complicated because there's all failure condition, but like the concept is quite simple, like fence and then repoint. And for the orchestrator hook to know which ProxySQL needs to be reconfigured, what I did is I'm storing the list of ProxySQL nodes and the host group on ProxySQL to reconfigure in the database themselves. So when the hook is contacting databases, it can also learn the list of ProxySQL nodes. So that's it for me. Like now, like these diagrams should like make sense to you. you should understand like the reasoning behind this. And so like I hope you learned something here. And so one last thing, like the talk is almost perfect service discovery. So what I mean by almost perfect here is that it protects against split brain. So the perfect scenario here in service discovery is that it never points to the wrong primary. Like obviously there are trade-offs here, and the trade-off for like always pointing to the right primary and avoiding split brain is the risk of not being able to fully reconfigure service discovery if we're not able to contact one of the fencing. But I think this is an acceptable trade-off if your like data consistency is of high importance for you. And now I will let Art talk about the lesson learned running this infrastructure. To you, Art.
All right. Let me share my screen first. Yeah. All right. So Jean-François already gave me a short intro during the beginning of the presentation. To begin with, I joined MessageBird in 2019 when the rollout of this whole service discovery happened. So there were still a lot of components that needed to be added to this system, a lot of components that need to be tested. So that's also where I'm getting all these learnings from and that I'm sharing with you. A short talk about MessageBird. First of all, I have to make a disclaimer that any of the opinions that I have in this presentation are not shared by MessageBird. That's nowadays obligatory for the size of our company to tell that, but I can tell you that basically as an engineer, I stand fully behind all my own opinions. MessageBird itself is a company that is sending out messages on various channels like SMS, email, Facebook Messenger. We have WhatsApp integration, and you can reach or you can send those messages via APIs. And I've done a talk about one of these APIs earlier today. So you can refer back to that presentation more about what we do as a company. With that said, let's move into how we feel about the service discovery. And to be honest, we have been successfully running this in production over 2 years now. And obviously, we had a couple of failovers and switchovers happened. We never had any issues with the multi-region failovers. It's all automated and it happens just automatically. And most of the time, whenever the primary comes back up, we just simply switch over back to the primary region that it was in the first place. That saves us a lot of trouble reconfiguring master gateway and fencing. But most of our workload is actually in single region primaries, so that's logfen. And that also means that most of the things that I'll be mentioning here are applying to single region primaries, and I'll be talking a lot about collect and logfen and not a lot about collect master gateway fencing. Small word about ProxySQL. It has been very stable for us so far. We started out with 1.4. We upgraded to 2.0 in a cluster, and we're now running most of our ProxySQL in 2.1, which is only, I think, a few months ago released, and we're happy with that. Why are we happy with our service discovery layer? Well, it's a lot easier for our developers to set up connections to the primary and scale out reads. In the past, at MessageBird, the connections were set up by applications by having a primary and a failover that were in circular replication. And that way they ensured that if they started failing the application over on the application side, they would ensure that they could still write to a primary. And of course, circular replication is something you never should do. And I think Jean-François already did a very good talk about that in the past. And otherwise, his blog post is excellent to read on his opinions there. But we now have a single point of entry. So it's very easy for a developer to just set up the correct connection details, and they don't need to care about failover handling. And similarly, for scaling out reads, they don't need to keep a list of all the IP addresses of our replicas either. And even better, we can use differences in read. So we can, for instance, have read only on replicas, read only with a replica bias. And we can differentiate that by creating new host groups in ProxySQL. So one of the first downsides we found in the ProxySQL setup that we have with a multi-layer ProxySQL setup is that multiplexing is quite tricky to do. So without multiplexing, connections that are incoming will be on a 1-to-1 ratio between collect and logfan. And that is perfectly fine unless you start doing a lot of connections that aren't being used at all. And in our case, we had an application that was making connections to each and every shard that we created, even though they were only using one at the time. And by now, we already have 8 shards in that system. That means that there are 7 out of 8 connections unused. That also means that it creates a lot of connections to ProxySQL, and ProxySQL is getting quite busy handling all these connections. With multiplexing, you can actually start multiplexing those connections over existing connections. So theoretically, those unused connections can be reused by other connections that are incoming and are using those connections. So the multiplexing happens between collect and logfan in this case. Also, it could be even lower due to having less overhead of establishing new connections between collect and logfan. So that's another positive thing. So prior to multiplexing, we basically saw a picture like this. We had about 2K incoming connections into ProxySQL, and outgoing connections on collect was 1.4K. When we configured multiplexing in our configuration, not much happened, and we couldn't figure out why that actually was the case. And here we started digging into all the smaller details of ProxySQL, starting to figure out what are the boundaries of multiplexing. And we found that actually ProxySQL is disabling multiplexing whenever it encounters an auto increment. This was caused by a bug report on Hibernate, and Hibernate wasn't able to handle auto increments in a similar way as PHP or Go are doing it. PHP and Go are parsing the OK packet of MySQL, so that's the response packet by MySQL server that it incremented the last auto increment that it created during the last transaction was X. By parsing that OK packet, basically the language like PHP or Go will know that the auto increment happened. Hibernate isn't able to do that, and therefore it issues a query to get the last auto increment. And by doing that, it means that you cannot multiplex those connections, because in the meanwhile, another connection could have been multiplexed over it and has created a different auto increment. So that's where ProxySQL decided to disable multiplexing to make it more safe out of the box. And by doing that, it set a default of 5 for the auto increment delay multiplex. And this means that for 5 consecutive queries, multiplexing is disabled. In our case, we had a lot of auto increments happening, and our auto increment ratio versus normal query ratio was about 1:3, 1:4, and that meant that we hardly ever were multiplexing. So after we had changed this setting, because basically this setting is perfectly safe on most of the programming languages, we were able to get a 1 to 100 ratio of connections. That was a very big win. However, while we were growing as a company, we started adding more and more workload on our collect layer and on our logfan layer by reusing collect and logfan as much as possible. So every new application or database that we integrated into this stack was all put on the same collect and logfan layers. And we scaled the collect and logfan layers accordingly by just adding more CPU, adding more memory. The reason for doing this is that centralized configuration of ProxySQL is more favorable than having many ProxySQL instances that you have to configure with host groups and users. But this was something that was kind of a mistake to do, because while we were doing this, we were finding all sorts of smaller issues. One of the largest issues we had was noisy neighbors. So imagine there are multiple host groups, and those host groups have a certain workload, and that can influence the performance of other host groups in the same ProxySQL. We also wanted to reduce the risk of running a single stack. We wanted to be able to tune better for particular workloads. We wanted to have a bit of easier maintenance because we have a single stack of ProxySQL, a single collect layer, single logfan layer. We have nothing to fail over to. And then we also found a cascading effect that it could have to other host groups, and that's kind of a war story. So currently we are running 3 vertical stacks of collect and logfan. We also have another stack that we're currently building that is integrating into an existing logfan. So we have a different kind of collect in front of an existing logfan. To start about our separation of stacks, noisy neighbors. We found that ProxySQL will show increased latency if you get above 50% CPU usage. And this is natural because if the CPU gets more busy, it gets ProxySQL can't handle connections as fast as previously. We tried to lower CPU usage by multiplexing, so lowering the number of incoming connections to logfan, for instance. We lowered CPU usage by enabling idle threads, which is a very good way of getting rid of connections that aren't doing anything. So this was on the collect layer. But still, we would get on the logfan layer some issues where a certain API would get 1,000 times the normal workload. I've done a presentation about that earlier today. And then the CPU usage can get above 50%. So that means that we are adding latency on the entire logfan layer by increasing the CPU usage on one single, we're increasing the CPU usage due to one single host group. And that also means that this latency will cascade upstream to the collect layer, and that will cascade into the applications responding slower. In these graphs, you can see that we have the number of connections incoming that is increased. We see the CPU usage spiking to near 80%, and this is during one of those 1,000 times normal workload. We also wanted to reduce risk. Unfortunately, during one of the incidents, we found out that our TCP limits were about 12K established connections per ProxySQL host. And that means that if you are nearing that TCP limit and you will get increased latency, you will get more and more errors happening on the TCP level, but I'll get into that later. So that means that we have a physical limit of 12K connections per ProxySQL host. Our collect layer reached 7.8K connections at a certain moment. per ProxySQL host. That means that we are about 1/3 to the limit. So that means that if one collect host would fail, we have only 2 that remain. And 2 remaining hosts will then have to do a 3.9K additional connections per host. And that is very close to the 12K limit. And that obviously means that we immediately need to repair this host. So even though we designed the system to have, like, okay, we can deal without one of the hosts in any layer, and we'll fix that on Monday, it all of a sudden is like, hey, one of the hosts is broken now, and now we need to fix it immediately. So that was not a very good point to start. So that's mitigating the risk. There's also another risk. ProxySQL will keep count of connection errors and will start to shun hosts if they become less responsive. This happens on host groups with any number of hosts. So whether it's like 3 hosts, whether it's 1 host with only a primary, it will just happen. It will shun the host, it will remove it. So once you start nearing those limits of the TCP, you could trigger this as well. So errors to LogFan or master gateway will increase, and that means that LogFan and master gateway backends will be shunned. And that also means that established connections will also be closed on those hosts, but more about that later in the war story. These graphs, you can see this kind of happening. So we have the connections incoming increasing, we have the CPU usage increasing to almost 80%. And then we can see that on the right, we have connection pool errors happening on this collect layer, which is, these are only 2 errors, and it's not that bad. And believe me, it's not that bad, because we've also seen things like this happening. And this is on LogFan. So this is not between collect and LogFan, but this is from LogFan going to the primaries. But we see a lot of issues happening like this if we near the TCP limits. So this is more scary because that means that a lot of hosts are constantly being pulled out of the host group and entered again. More about here, shunning of a primary. So like I said earlier, ProxySQL keeps count of those connection errors, and it also happens with primaries. For a primary, it will not listen to the configurable you can set for the number of seconds a host needs to be shunned, but it will shun it for only 1 single second. But even shunning for 1 single second could create another torrent of connections. In our case, we have applications that are constantly running and constantly trying to send messages. So they're in an endless loop. So whenever the database connection breaks, it reconnects immediately. That means that if we start seeing issues between collect and LogFan, the connection to LogFan is then paused for 10 seconds. But after 1 second, the primary becomes available again. And that means that between collect and LogFan, we have accumulated probably thousands of connections waiting. And that means that this torrent of connections is incoming into the primary, and the primary will not be able to cope with that workload and immediately starts to show connection errors and is being less responsive. So you get into a loop. We were able to detect shunned hosts only by scanning our ProxySQL log. Luckily, it includes a server name, it includes the error rate, and it gives you a hint on the duration of the shun. We created a log tailor that is basically looking for connection timeout, shunned host, shunned due to replication lag. That's also a case where it happens, to distinguish between a primary and a replica failing. And we export these metrics to Prometheus every minute. And that gives us a very good indication on how frequently this happens. So these are the graphs that we draw from them. You can see the connection timeouts happening. Those are being counted. We are seeing masters and replicas being shunned. And that gives us more information on what is actually happening and where should we look at. Finally, for shunning a primary, if we are shunning a primary for 1 second, it will also create an avalanche of incoming connections. Normally, we have a latency of maximum 10 to 50 milliseconds on the total duration of a connection running the queries. And now all of a sudden we have added latency of at least a second. So that will decrease the application throughput. And that means that Kubernetes will scale up workers. And if Kubernetes is scaling up workers, that also means that we have more incoming connections. So that is not a very good outcome of shunning at all. I mean, we're just increasing workload and workload and workload. So how did we deal with this? During one of these incidents, we started thinking about it. It's like, okay, we just start hitting very hard on our primary. So we need to throttle down the number of workers. So now most of our applications have a fixed ceiling that they cannot exceed. And of course, we can fix this by decreasing the number of connections that are possible in ProxySQL. But if we do that, most of the workers will get a max connections error, and we'll try again and again and again and again. We will not solve the problem by doing that. Another reason for separating those stacks is better tuning. We have seen that most of ProxySQL tuning is done on a global level. And some examples here are the connection delay for multiplexing, the number of free connections we keep in the connection pool, the wait timeouts. And that also means that those are global. And if we have a separate need for a different host group, or even have a host group that needs some fine tuning, we cannot do that on one big stack. So that's why we wanted to have smaller collect and logfen stacks to be able to fine tune that for the workload that we do. Another reason to do the separation is maintenance. Maintenance is always scary to do. Draining from a Google load balancer is basically closing after X minutes, but a lot of our workloads are still running queries that are longer than X minutes. Also, being near capacity means that we run a risk of creating an incident while performing maintenance. And that's even worse because you're busy on fixing an instance or upgrading an instance. And now all of a sudden your highest priority is to get this instance up and running as fast as possible. Also, maintenance on master gateway fencing logfen is scary because draining a host can take ages to happen. And this is due to reusing connections in the connection pool. We have a connection timeout of 8 hours. And that means that while that traffic is still flowing, those connections are still established. So on collect, we have a timeout of 8 hours, which then propagates into the connection pool having a connection timeout of 8 hours. And as we are reusing those connections and multiplexing over it, that is like an endless loop. Also, some of our applications don't handle closing of a connection very well. And that's another reason why we like to avoid that. So now we get to a situation where we rather have an application redeployed to a different stack that has been upgraded. And then, of course, they don't need to do anything but just a deployment to a new stack of collect and logfen. And then once we have migrated all the workload, we can probably get rid of this collect and logfen layer instead of upgrading it and performing maintenance, but just deploy a new one. The final reason for the separation of stacks is the cascading effect. This is like a war story. We had instability on one cluster that swiped out many others. So this is a combination of everything that I mentioned before. The instability started on a cluster that had a backlog setting that was too low. On TCP level, we also didn't tune properly, and that means that once MySQL is not able to create more connections incoming, it starts to outsource that to TCP, and TCP quickly then overflows on the primary. ProxySQL then starts to shun the primary, and in the effect, we got continuous shunning happening, like I said earlier. This affected the stability of other host groups. And why that happened, you can see here in this graph that we started to shun hosts a little after 1512, I think. And we started to also see connection timeouts happening to all sorts of other hosts. If we look at the listen overflows of that particular ProxySQL layer, so this is the ProxySQL layer that got affected by the outage, we start to see TCP listen overflows happening on ProxySQL hosts as well. So that makes it even worse, because if that happens, we are near the TCP limits of ProxySQL. And then in effect, collect will start to shun Logfare as a whole. So basically your isolated problem on a single primary now starts to cascade into all of your host groups on Logfan. And that's not good if you're running a lot of different workloads on a single Logfan. Finally, we have a couple of other concerns or quirks that we found on having a multiple ProxySQL layer. One of them is connection contamination. Whenever a connection is being made between collect and Logfan then makes a connection to the database, these client connections will be reused. I've described that earlier. ProxySQL resets a connection to the initial connection parameters after it has closed the connection on the client. It will then be put back into the connection pool, and then the connection pool has a fresh connection with initial settings. But if a new connection comes in on the collect layer with a different setting, but then is reused over a connection that, sorry, I'm saying it wrongly. So that connection is then reused on between collect and Logfan to the database. Those connection settings don't necessarily have to match anymore. So normally this works fine between a database, an application, ProxySQL, and a database, because in that case, all of them have the exact same settings like UTF-8 and MD4 or a CT time zone. But if you have a double layer, that doesn't necessarily be the case anymore. So by fixing this is very simple. You have to go through your code base and get rid of all these quirks that are being set manually somewhere inside a query. Another final quirk that we found is uneven distribution. Because a lot of connections are being reused, ProxySQL favors using an existing established connection. And that means that if a connection is available on one host, then it will favor that over creating another connection on a different host. This is influenced by the number of free connections percentage, which is a global setting. And in some cases, we have a host group that allow, let's say, 3,000 incoming connections, because we expect it to sometimes have a workload of 1,000 times the normal workload. 2% of 3,000 is 60 connections, so we keep 60 connections open, but our actual workload is only using maybe 10, 15 at a time. And that means that we are keeping more connections open than necessary in that connection pool. So ProxySQL always favor like host number one, which has an available connection. And that way we see that one host is being used a lot more than another. Of course, you can fix this by closing all the connections of these host groups and restart from the start, but that's a whole different story. And that concludes our presentation of the service discovery at MessageBird. I hope we have made everything clear how the system works and all the boundaries that we found with this system. And in general, we are quite content with it, and we are definitely going to use this in the upcoming years.